And let's continue from the point where we stopped it. Right now, what do we see? We see the same slide we stopped it. It comes about aerodynamical principle of flight, and and this aerodynamical principle of flight has name of Bernoulli. Another name, it's Bernoulli principle of flight. How it happened that it was named after Bernoulli. Daniel Bernoulli, as I already said, it was prominent scientist of 18th century. He was born in 1900, and in 1978 he has printed his book. He issued book, a well-known books, Hydrodynamics. You see the front page of this book. Why it's Hydrodynamica? Because it was originally issued in Latin. Latin was language of scientists all over the world then. And typically they use it an international language. And one of things that was stated in this book, it was another theory of air at all. I already have mentioned Newton in my story, and to be frank, I'm already trying for fourth or fifth time to record this thing, so can't say exactly which version you heard from me. Newton, also prominent physicist, and he has studied a lot of things, mechanical science, including the aerodynamic. In particular, he studied the flow and the body placed in the flow, how they interact, body of different shapes, and he proposed some mathematical formulas for calculating the forces. Actually, in engineering calculations, his formulas almost in the same way as they were written, used for engineering calculations, not for scientific one. But by now they have name. No, in our country they completely called formula Zhukovskого. In international society, they usually called formula Newton. About these formulas we will talk later. Right now, not about it. Newton had an idea about air. No, do remember it was 300 ago. People do not understand real structure, real arrangement of our universe. And by that moment, different ideas exist, different concepts. And one of them, it was a concept of corpuscular theory, that any media actually consists of little bodies, something like little balls. And Newton considered this air, liquid, not like continuous media. He considered it like a collection, let's say, of tiniest balls. And he created his formulas, his theory on this basement, let's say. And Daniel Bernoulli, in contrary to them, he has proposed the theory of continuous media, and liquid and air. He considered it like continuous flow. And in the plainest words to say. And one of his experiments was with parameters of those flows of these fluids, let it be liquid. Actually, it was liquid, of course. That how it's interacted, the speed and pressure. Speed, pressure, and another parameters inside of this flow fluid. And right now you see in front of you the picture that demonstrate one of his experiment with fluids, with liquid. Pipe of different cross-section. In some pictures, in some variants, you might see it even more complex shape, spatial shape. I will show you a little bit later, maybe. And what is different? Different is cross-section of this pipe. Somewhere it's narrow, so-called bottleneck and somewhere it's it's wider. And quite clear. No, once again, remind you, this theory is about so-called ideal flow, ideal liquids, ideal gases. It means that they are incompressible and they are no, non-separable, and it comes about the flow of constant volume somewhere inside of some path, let it be. And due to these properties, due to these simplifications, quite clear that if somewhere here you have wider place, the same volume of liquid has rather low speed comparatively to this place where you have bottleneck, where the liquid need to squeeze through this bottleneck, and of course, in order no, to continue the flow, it should be with higher speed, higher velocity. And when manometers join it to different places of this pipe, what does it show? That where we have slow motion with low velocity, with low speed, we have higher pressure. Where we have higher speed, higher velocity, we have less pressure. Actually, Bernoulli have studied and he has proposed mathematical description, mathematical formula for what he has studied. He studied one of particular cases of principle of energy conservation. What we talk about right now, it's one of particular cases of energy conservation principle. The most general principle. In the plainest words, this theorem states that energy of flow along some path stay permanent, stay constant. And the mathematical formula, the mathematical description of this idea looks like this. You already seen it, and once again remind you what it's about. Let's see this slide a little bit more. Practical is the same pipe without manometers. Cross-section number 1, cross-section number 2. You see cross-section number 1 has wider area, wider greater area, if we imagine the pipe, and cross-section number 2 has less area. And on the right, energy is written, and on the left, energy is written for these different cross-sections. What we see, Bernoulli has separated, has split it, let's say, this energy, and wrote that energy consists of 3 components. Pressure, which he might see in manometer, some portion of energy that must remind you what kinetic energy, literal rho here, it's it's density of media you work with, and in the way mv squared by 2, you know it like kinetic energy of some material body. Yes, here this material body instead of mass, it's given density. So kinetic energy of the flow, and so call it attitude energy or potential energy of the flow. Now, in my opinion, it's not ideally correct to call them here. No, we know that we have kinetic energy and potential energy, yes, and some third energy has appeared, pressure energy. And in different sources, you might find the same formula, but with another names of these components, because typically people call it in English, they call it static pressure, kinetic pressure, and attitude pressure. Once again, it comes about energy of the stream, energy of this flow. Energy is constant in different cross sections. That's it. And energy consists what it's spent for, how it's demonstrate itself in pressure, in kinetic energy that depends on speed, on square of speed actually, and on height. In our case, next, we may not even notice this last component, attitude, because it's something similar to what we see, that flow is on the same height. Wait a second, I already did it sometimes today. Yes, this picture, the same story, but pipe has changing of attitude. In this case, of course, it's necessary to consider also attitude energy changing. But as we are talking about the same heights, we may not even remember about it right now. Just remember this pressure and velocity. It's enough to understand some things. And how it's related to us. No, first, I would like to show you a couple of short video explanations in order my story would be not so boring. Uh, it's demonstration of Bernoulli principle. No, of course, it's not my video. I take it in internet. What we will see here, you see man, experimenting man, what he doing? He has little pipe and he create stream through this pipe. See, he blow through this pipe, you understand? And what happened next? Ball, ping pong ball, quite clear, as only he removes the hand, ball should fall down. No, ball does not fall down. You see, it's holding by this stream of air. But to pay attention, it's along the stream. Yeah? It does not, no, it does not try to escape to the right, to the left, because it's symmetrical body. Not quite the same. This boy demonstrate. He show like no child working with the hair fan. You see. Next, he will demonstrate it with higher size and higher mass, but it comes still about these symmetrical bodies, and it's also actually it's demonstration of Bernoulli principles, but also it's considered like effect of Coulomb effect. Maybe if you already studied aerodynamics, you know this, at least these names, you know. What is next experiment about? Actually, something similar we usually do in our offline classes. And look, man will try to align these two cans. Cans made of aluminum, everyone know that they practically have no weight. He aligns these cans on some distance from each other, and next he blow between them. When you blow to something or between something, what you expect to get? What result expect to get? Maybe this something will move away because you're blowing between them. And usually students answer, no, 17, 18 year students who study those things for first time, they do not try even to apply newly taken knowledge or newly received knowledge about Bernoulli principle. They answer that, of course, these scans will move away from each other. Let's see experiment demonstration. He placed it close to each other, close enough in order to have this effect, and blow between them. What happened? In contrary, they move to each other, not from each other, but to each other. How it's happened? How it's in line with Bernoulli principle? Very simple. Look, where no from different places. What imagine here and here you have two cans. Where you increase the speed when we blow here with some higher speed. Where we increase the speed, there we reduce pressure. And pressure outside remains constant, remains the same, stationary. Pressure inside reduced. Of course, they move to each other. And the same experiment, but with another objects. Something similar we usually do with pieces of paper in class. Look, boy blowing and they are gluing to each other, adhering to each other in order, instead of what we wait for, that they will fly away. Yeah? That was demonstration of Bernoulli principle, what it looks like. And one more thing I'd like to show also. No, its animation, of course, it's not real experiment already, like in real, but it's possible to see something at least.
Of its particles.
Theorem of
Bernoulli
Bernoulli
states that the
here,
total
you
energy
see
of a
how it's
small
stated.
amount of an incompressible liquid flowing from one point to another remains constant throughout the
No, I'm
displacement.
afraid you don't hear the sound, and I will reduce even the sound. Next. What do they show? It's animation of the same experiment that we have already seen as a real one. And next, there is explanation how it's work. And this experiment, very interesting. And device is based on this Bernoulli principle and Bernoulli. No, let's see. He is the author of idea practically of these devices that you permanently use in your everyday life. How it will work? Look, some pipe, it's placed into liquid. Of course, liquid level in pipe and in this vessel, they are on the same level. Quite clear. It's obvious. But as only you start blowing through another pipe, which is joined here to the thin pipe, what might happen? Do apply now your knowledge of Bernoulli principle. What will happen? In this place, speed will be much higher. It's bottleneck, squeeze it through the air, squeeze through this bottleneck. And as here in this particular place, it will be much higher speed, it will be much less pressure. Pressure around yet the same, and pressure in this place is very little. What will be in this case? Liquid will be sucked into this thin pipe and move up. Now they show, they explain it and show animation.
The pressure at that point decreases below the atmospheric pressure.
Afraid to click it because it will be too far. Oh, you see. Water move up. Water or some another liquid, perfume, for instance, or some liquid for washing the dishes, for instance. It's moving up. And you know those devices. You all use them in your everyday life. Application of these devices, of this principle, is in so-called atomizers. Well, maybe another no, into airfoils also, no, doesn't matter. In other devices, maybe you do not understand, do not recognize, but those things you use each day. So you are working with Bernoulli principle practically each day. Так, let's switch it off. And how it's applicable for airfoils? No, for flight, not even for airfoils, for flight. As I'm already said, some person has have experimented with shapes, with different bodies of different shapes, which are placed inside of some air, liquid, whatsoever, some flow. Maybe they were not interested in flights then, maybe, but at least they've been interested in, ships, sea vessels, sea vehicles, sea transport, and it's at that period those field of engineering also been quickly developed, and people need more theoretical knowledge in order to simulate, to model some situations before it happen, in order to predict theoretically what they may got in practice next. And it was provided a lot of experiments, and one of these experiments has finished up with understanding that some body which is placed in the flow, in case it has no symmetrical shape, if it's non-symmetrical, it's maybe even flat plate, flat thin plate, but placed non-symmetrically in the flow, that this body may create additional force, like pushing force, lift, may be created due to such a body placed inside of the flow. No, this theory that explain it and how it's explained, we will see right now. And no, let's see how it's explained. It actually, even in this place, theory says, according to Bernoulli principle, as we may understand, once again, it comes about the endless wing, about the endless airfoil object. It's we see the segment, one cross section, but it's ideal case, theoretically, or sorry, ideal case, and it means that this object is endless to the no to well, you imagine it, endless wing. Uh, is it possible to imagine? And flow itself, it's so-called ideal flow. It means that it's incompressible and inseparable. And according to the flow as continuous media, according to this fluid as continuous media, what happened? No, some streamlines here, what in this picture on the left, you see streamlines that meet the body, let's say. They are separated, yes, on the body, but it's not possible to separate the flow. And it means that moment when upper streamlines and bottom streamlines meet, it should be the same moment here at the trailing edge of this airfoil. And in order to meet, those who walk, let's say, who pass along the bottom, they have shorter distance to pass. And those who walk along the top surface, due to non-symmetricity of this airfoil, or due to its changed position, like you see it right now, that it's rotated with respect to the horizon in the floor. Because of this, they are distorted, and here is the longer path to pass. And quite clear, the longer path for the same time, it means that here we have higher velocity over their profile, we have higher velocity. And what does it mean, higher velocity, if we recollect Bernoulli principle? Quite clear, it comes about less pressure. So pressure under the profile, under this body, is higher than pressure over this body. And this difference between pressure on the top and pressure on the bottom, it's create lift. Well, everything simple, everything is explained. Moreover, Newton has given the formula even which explain, no, not explain, sorry, formula which help to calculate both lift and drag. The because actually the force due to this specific shape, let's say, force is not directed like this vertically. Force directed with some angle, and somehow similar to what we have seen in remind me in no, whatever rocket dynamical principle, ballistic principle, when some one vector, what for instance here thrust vector applied to the rocket, and it's maybe composed, it's maybe splitted, decomposed onto a lift conditionally and onto the force that move this rocket front. You see, it's already appeared one more picture because it's already appeared twice here. And this time I do not delete it. This aerodynamical picture. Well, what does it mean once again? Here, the force really directed with some angle, and we decompose this force. On one hand, it's a force of lift. On other hand, it's force of drag, which counteract the motion through the flow. But, what is the truth? Oi, look at this. Truth is, it's not true. This theory, which uses direct explanation, what really direct explanation according to Bernoulli principle, Actually, Bernoulli principle is completely correct, but only for ideal gases. Yes? No, for ideal gases, ideal liquids, ideal fluids. And with respect to flowing around the some profile, it's also correct under some, not quite correct, under some simplifications like endless wing, ideal fluid, and so on and so forth. But in real life, this theory is incorrect. And in case we try to use immediately formula of Newton, all our calculations will be wrong. Next, this formula was a bit changed. The formula that you have not seen yet, no, at least in my explanation, it was changed, and it was changed by Zhukovsky. And Zhukovsky and one more man in Germany, independently but almost in the same time, they have explained the nature of lift, and they express it in mathematical way. They prove it like no, like theory which proven mathematically, and even has obtained the shape of this airfoil, what it should be. It was Zhukovsky, Nikolai Yegorovich Zhukovsky, and Kut. Or I need to check how it's pronounced in English. Do forgive me. Maybe I pronounce it wrong right now. Kut and Zhukovsky, they independently and almost at the same time, they have found mathematical decision of this problem. A little bit more complicated, no, with respect at least to Bernoulli principle, not so simple to understand that theory. Right now, it's not our problem. We are not talking about it. We're just talking about the flight principles, once again, remind you. And as to the flight principle, this Bernoulli principle, this aerodynamical principle, help us to understand how lift may appear here due to different pressure over the wing and under the wing. But why pressure is different? Because speed is different. But why speed is different? It's another story. It's a story about circulation of vector of speed. Not right now. But whatsoever, it's easy to remember, easy to imagine how it's work. Higher speed, low pressure. Lower speed, higher pressure. And this difference of pressure create us additional forces. But under some conditions. Above the all, it's not possible in vacuum. No streamlines, no flow, which flow around the shape, no motion of flow, yeah? No forces. Moreover, when it comes about symmetrical bodies, whether it's sphere, whether it's thin plate, for instance, no forces. And it means that if we'd like to have aircraft which realize aerodynamical principle of flight, it should have specific shape of some surfaces. And no, you have already seen it in a picture here. This lilac color. Rocking. This lilac color of no, something like airfoil. I tried. Yes. 4 forces acting, you see. And we need, once again, surfaces of specific shape joined to the some material body, whatever body. It's maybe even automobile. The question only in velocity you need to develop for this automobile, and in the area of wing which is necessary to move up this automobile. Whatever, once again, body that move through the air, or through the liquid also, through some fluid, the shape is responsible for appearing of this lift. And in this case, we may realize aerodynamical light where our slides are. And such devices, such type of aircraft, they are well known to you, of course, in different ways. Look, the very first of them, of course, are airplanes. And Z1. Z1, it's not airplane in clean understanding. We already met it at the beginning of lecture. It's a glider. Glider is combination of aerodynamical principle and ballistical principle. Ballistic principle. So glider is hybrid flying vehicle, let's say. And there are so-called fixed wings aircraft, like airplanes, for instance, or Z1 screen, seems like screen. It's called ekranoplanes even in English, maybe because it's first appeared in Soviet Union and because this name directly came from Russian language to their English. Even in English literature, it's called ekranoplane. Directly translated, maybe like screen plane. This one, it's like flying saucer, да, it's called UFO object. They are usually fly near the ground. They are huge. They may be huge. They are able to carry huge cargo, big payload, and so on. But they have limitations. This thing may, no, as it's use additional effect, a so-called ground effect. It's something like reflection of air from the ground, which create additional force, additional lift to such flying machine. But these screen planes, ekranoplanes, they are able to fly effectively only over the flat surfaces, quite clear, and not on big heights. On higher heights, it just lose its additional advantages, additional bonuses, let it be, from ground effect. What does it mean, flat surfaces? It's maybe desert, it's maybe polar area, it's maybe sea surface, for instance. And in this case, such flying machine is extremely effective, much more effective than airplane, for instance. I'm talking about the coefficient ratio of payload to the whole weight of the aircraft. So airplanes, gliders, ekranoplanes. What do we see right now? And I'm afraid you know only word helicopter. They are so-called rotorcrafts. Some of them are really clean rotorcrafts. These surfaces, no, surfaces of specific shape, they either move linearly through the air due to engine, for instance, or they may be moved through the air at the place immediately by rotational motion. So they, no, practically they stay on the place, but air flow you provide due to rotation of these specific surfaces. And as a result, again, you have some force which directed to the top, lift on each of these surfaces. And mostly we understand it as helicopters of different schemes, helicopters of different schemes of rotors. Uh, Positions of rotors, amount of rotors may be different, but there are also called hybrid aircraft. One of them is autogyre. Typical autogyre we see here is something intermediate between the airplane and helicopter. What is the difference? Helicopter has driven rotor. Helicopter rotor is driven by engine. It's rotated by engine, and autogyre it has rotor like helicopter, but it's not driven. It has engine, maybe prop engine, for instance. No, usually it comes about little speeds and prop engines. Uh, Prop engine and engine with prop whatsoever. It's maybe a piston engine, it's maybe jet engine. It's fantastic, of course. Usually it's piston engine. Piston engine with prop. and it has wings, but these wings are insufficient in comparison to the normal airplanes. These wings insufficient, not so big, and they are not enough to create the proper amount of lift. What is proper amount of lift next time? But when it start move through the air, due to this linear motion, this rotor also start rotates, and rotor create additional lift force. That is autogyre. What are gyrodynes? They are rather similar to helicopters. They have differences. Again, not now we're talking about these differences. They were popular in 16, 17 years of previous century for developing and using. No? Right now, they are practically not in use. And moreover, it's not even exist. This word exists in English, not gyrodynes. It practically does not use in our languages, for instance. Once again, aerodynamical principle realized due to joining special surfaces to some bodies, special surfaces of special shape, and due to motion with appropriate speed of the surfaces through the air. And in this case, you have additional force lift. And to outline what we talked about during this first class, once again remind you that lift is a force which keep objects, not kept, keeps object in the air, and lift may appear due to the different reason. And because of this, by this nature of lift, we have classification of aircraft according to four principles. Ballistic, when no, ballistic and aerostatical, once again, remind you, no engines. No engines, it means that no renewing the energy, the pushing energy during the flight, let's say. Ballistic, it means someone apply initial force. In case this force a bit deviated with respect to the horizon, you have decomposition of vector of motion, and this decomposition of vector conditionally may be considered like lift, and some pushing force which move object front, but it's forward, but it's disappear. It's like permanently spending during the flight, and as it has no engine, no supporting, let's say, of this initial energy. This energy is just spent to counteracting to the drag and to the gravity force. So ballistic flight, when you throw something, shoot something whatsoever. Aerostatical flight, due to the buoyancy force. What is buoyancy force? It's one more name of this principle, once again, Archimedes principle. Buoyancy force, it's a force that equal to the weight of media which replaced by your aircraft. Maybe difficult in explanation. Let's come back to that picture that illustrate buoyancy force. That if body inside of some media, no, here it's in a liquid, when body inside of some media, it takes the place of this media, and the force which media trying to push it out with, it's equal to the weight of media, of this liquid, gas, air, whatsoever. It's maybe also about liquid metal, for instance. I mean, buoyancy force of liquid metal, and weight of displaced fluid, weight of displaced media equal to this buoyancy force. This principle in clean way realized only in the aerodynamical devices. Sorry, not aerodynamical, it's my mistake, it's rough mistake. Actually, it's in air devices which are called air balloons. Once again, where is it? Air balloons, and no, the limitation you do remember. In clean way, originally, it may only climb and descend, so it's uncontrollable, seems like, in horizontal plane. But really, modern air balloons, they are controllable, of course, and somewhere here, but I do not remember now where. Uh, have shown you that picture. You have seen two different types of. Right now we see Montgolfier type, but exist additionally Charlier and Rosier types of air balloons, and they of course all controllable due to special additional devices included in design of such things, in contrary to the first versions. And one more interesting type of airship of aircraft is a dirigible, very popular at the beginning of 20th century, as I tried to explain you, and next practically been taken out from operating because of no, of specific reasons. But now interest has appeared again to this type of aircraft. They already work according to, they also hybrid aircraft. They work according to different principles. They use at least aerostatical principle and aerodynamical principle as well as they use engines. And they use additional surfaces and due to the motion of that body of through the air, like directed motion, forced motion, driven motion through the air, the linear motion of this body, lift also has appeared additionally. So, aerostatical air balloons and dirigibles uh, seems like toys actually, but they are not really toys. They are very useful and permanently used in our everyday lives, either, including such a thing like aerostatical principle for aerial probes. Yes, those little aerial probes who responsible for providing the information about state of atmosphere, and on their information we may do so-called forecast, weather forecasts. No, rocket dynamical principle, quite clear, very well known how it's used for space rockets and for missiles. And aerodynamical, it's the maybe most usable by now and most applicable in our peaceful life, and not only in peaceful life, that we have a huge amount of military airplanes all over the world. But maybe aerodynamical principle is the most usable principle now in all the types of aircraft. No, at this point we finish in order to continue next class.